Uh, Hello, engineers. Today I'm going to talk about integrity requirements as per ACI 31819, and I believe the same provisions are available now in ACI 31825. These requirements are mandatory and must be satisfied always in all projects. I believe in UAE, especially in Dubai, most of these provisions are automatically satisfied as we are providing a lot of reinforcement in our structural members, especially or because of the local authority requirements. But today, uh, let's talk about these requirements. First of all, if you would like to read more about this topic, you can go through these references. First of all, there are many buildings uh, collapsed totally because of local failure. ACI code uh, uh, is trying to avoid the progressive collapse due to local failure. So if one member fail in your structure, or if let's say one or two members fail in your structure shouldn't collapse totally. Initial or local damage in some buildings may cause a total failure of structure. In fact, this behavior is prohibited by the code. This building, Ronan Point building in the United Kingdom, 1968, as you can see here, we can see here a progressive collapse due only to a local failure. This building is a 22-story precast building, partially collapsed due to a gas explosion in 18th floor. This failure or local failure propagated down to other floors. 17 injured and 4 were killed only 2 months after it had opened. Weak floor, the main reason was weak floor wall connections. Building regulations were changed. So here we have one problem, one local failure caused uh, this type of a progressive collapse. Uh, Here also in Oklahoma City, 1995, explosion of a truck pump. As you can see, this explosion destroyed an exterior column supporting a transfer girder, collapse of nearly half the RC frame building, 168 deaths. This is very big disaster. Okay, also in Boston, 1971. Here we have 16 floor concrete building, bunching failure at roof level. So here we have a local failure. Collapse after placing block in all floors, propagated all the way to the ground floor. This collapse caused a damage of 2/3 of the building. For this type of failure, or we have here 4 deaths, and this type of failure is caused by unbalanced moments transferred between the column and the flat plate. Elongation of bars was not proper. Effect tension capacity of the slab at failure stage. Also, there were no integrity details in this project. As you can see, this portion of the building collapsed totally. Current integrity provisions are intended to aid in redistributing gravity load after an initial failure. Assume that you have a multi-story building, and in this building, one of the column slab connection failed due to a shear. If you don't provide integrity requirements for this building, the loads of this column will be redistributed to other nearby columns. If the DC ratio to a shear is at limit, I will say design DC ratio, and you don't have margin for the redistribution of such amount of forces, progressive collapse can occur. In Dubai, for any building with height more than 300 meter, you have to provide a progressive collapse study. In fact, this is different than the ACI intent, but ACI, in fact, is trying to provide an integrity provisions. These integrity provisions will not prevent the progressive collapse, but will improve the behavior of the structure, will tie the structure all together to reduce the effect of local failures and to try to limit the spreading of local failures and to avoid the progressive collapse. But again, satisfying these requirements will not guarantee a full or will not guarantee preventing the progressive collapse, but in general the behavior will be much better. Again, here we are interested in gravity loads. I have not seen integrity requirements for seismic forces, let's say, but I believe that integrity requirements are very important for all types of loads. But most of the provisions in the code are related to gravity loads. Collapse of flat plate or flat slab floor systems may be initiated by bunching shear failure, column failure, flexural failure of the slab. This local failure can be extended to a progressive collapse. Here also we have another example for a progressive collapse. This building in South Korea, 1995. Progressive collapse of this building caused or resulted in 502 deaths and 937 injured. Cracks started at 50th floor on April. No serious action. Nobody was care about these cracks at that time. Cracks grown up to 10 centi, very big cracks. Columns collapsed within 20 seconds only. We have here $216 million losses. This amount of money is equivalent to 420 million at 2022. In fact, there were no reasons for that. Many reasons caused this progressive collapse, but the code is trying to avoid that. Here also, as you can see, if bunching failure occur at this connection, we or the load capacity or transferring mechanism will be lost totally. But if you provide a bottom reinforcement, as you can see here, the bottom reinforcement will keep a post bunching capacity after the failure. These bars will prevent the total collapse at this connection. and this will keep some loads transferred to the supporting column. This is much better than a failure or a total collapse of this connection, as this collapse will transfer the full loads to other nearby columns. That's why here, if we have a bunching failure at a specific connection or at a column slab connection, due to the bottom bars, we still have some post punching capacity to avoid the total loss of the gravity load, I will say, or we will avoid the loss of the supporting the total gravity loads at this connection. ACI 318 integrity provisions do not specifically address the collapse resisting mechanisms previously mentioned, intended to enhance the ability of a structure strength, redundancy, ductility, and detailing of reinforcement. Again, it's very important to keep some bottom bars continuous through the column slab connection to keep some post punching capacity after a failure. This will help very much to avoid transferring the full loads to other nearby connections, and by the way, we will prevent the structure from the full collapse. This picture, in fact, shows some details required as integrity requirements for the two-way slabs. We will discuss in next couple of slides. By the way, we will start from one-way slab in chapter 7. By the way, at the end of, if you open the ACI code, I will show you that. If you open, this is the ACI code. Here, for example, we have one-way slabs, two-way slabs, beams, columns, let's say. For one-way slabs, here we have 7.7 detailing requirements. If you look here, we have to find that something called integrity requirements. As you can see here, structural integrity requirements in cast in place one-way slabs. As here, if you can see here, the section is included in the main chapter of one-way slab. This means that satisfying these provisions are mandatory. Also, if you go to two-way slabs, also 8.7 for their detailing, we have to find here also integrity requirements. As you can see, structural integrity. Also, if you go to the beams chapter, 9.7 for the detailing, I will show you here. We have also integrity requirements somewhere here. I have to find, yes, here. Structural integrity reinforcement in cast in place beams. So they are mandatory. You must satisfy these requirements. Let's start with one-way slabs. 7.7 provision 7.7.7, I think this is commentary. Positive moment structural integrity reinforcement for one-way slabs is intended to be similar to that for beams. Okay. Provision 7.7.7.1, longitudinal structural integrity reinforcement consisting of at least 1/4 of the maximum positive moment reinforcement shall be continuous. As you can see here, we have, by the way, all the informations here are a copyright of ACI or the American Concrete Institute. Anyway, if you look here, we have 1/4 of the total positive reinforcement, total maximum positive moment reinforcement, they are continuous. This is very important. Longitudinal structural integrity reinforcement at non-continuous supports shall be anchored to be developed yield at the face of the support. If you look here, you see here we have some bars extended into the support. As per 7.7.7.2, these bars must be anchored inside the supporting member. Some engineers always think that the development length or standard hook shall be satisfied only for the top reinforcement. But as per the ACI code, and it is especially for the integrity reinforcement portion, not for all bars, also the bottom bars or the bottom integrity bars, because this is not required for all the bars, this is required only for the integrity bars, we must satisfy the anchorage requirements at the support. This is very important. By the way, this is for one-way slab. Again, for here the development or anchorage requirement cannot be reduced by excess reinforcement or by the reduction of development length for excess reinforcement. Some engineers think that, okay, if I am not able to satisfy the anchorage requirements at the support, I can increase more bars to reduce the stress. So this development length can be shorter. No, this is not permitted for the integrity reinforcement. We have here A, B, C, D, E, around 5 cases that a reduction of development length by using excess reinforcement is not permitted. You have to know that increasing the reinforcement more than the required will not allow you to reduce the required development length. One of these cases is at locations where anchorage or development for a field is required. So the integrity reinforcement is covered by this case. Okay, another provision for one-way slab integrity reinforcement. If splices are necessary in continuous structural integrity reinforcement, the reinforcement shall be spliced near supports. Here, if you cannot keep the bar continuous, at that time you can use splice, but you have two conditions must be met. One of them, the splice must be near the support. This is number one. Number two, class B tension lap splices must be used. Maybe you will think that at this location we are far away from the positive moment, that's why we can use tension splice class A. But for the integrity reinforcement, you must use the class B. You will ask me why? Because the bottom reinforcement is very important to prevent the progressive collapse by something called catenary action. By the catenary action, when excessive deformation will occur to the slab, the bottom reinforcement will prevent the total loss of the connections and the total loss of the capacity. That's why the code is trying to keep those bars continuous with a class B tension splice. Okay, all these requirements were for one-way slab. If we have a two-way slabs, we have a different requirements. Two-way slabs are covered in chapter 8. So here, all bottom deformed bars or deformed wires within a column strip, so all the bars within the column strip in each direction shall be continuous or spliced using mechanical or welded splices in accordance with 25.5.7 or class B tension. Some engineers always ask me, engineer, why you are specifying class B tension lap splice for all the slab? We can use class A. If you look for only this provision, the code requires all the bottom reinforcement within the column strip must be continuous or class B tension splices must be used, or you can use mechanical splices. By the way, this is not normal or the typical in the practice. In the practice, they are using conventional lap splice. provides the slab some residual ability to span to the adjacent supports should a single support be damaged. As you can see here, if you look, what the code need for two-way slabs to satisfy the integrity requirement. First of all, the bars within the column strip width must be continuous, or class B lap supplies tension, by the way, must be satisfied. Number two, minimum two bars must pass the core of the columns and must be bounded by the longitudinal bars of the columns. As you can see, these bars will prevent the total collapse of the slab, will tie the slab, and will prevent the total loss of the connections, will provide also post punching capacity. As you can see also, we have here another requirement. At least two of the column strip bottom, here I'm talking about the blue bars, these bars are bottom. Why bottom? Again, I will go back here. As I said before, as you can see here, the bottom bars will prevent the total loss of the connection. Here also, as you can see. That's why the code states here, at least two of the column strip bottom bars or wires in each direction shall pass within the region bounded by the longitudinal reinforcement of the column and shall be anchored at exterior support. Again, we have to satisfy the anchorage, not only for the top, also for the bottom reinforcement. By the way, this is not required for all bars. This is required only for the integrity reinforcement. Okay, now for beams in chapter 9, we have here additional requirements. Okay, for beams along the perimeter, here we are talking about the perimeter beams. You have to know that we have different integrity requirements for perimeter beams and for interior beams. For beams along the perimeter of the structure, structural integrity reinforcement shall be in accordance with A through C. So you have to satisfy all of them. A, at least 1/4 of the maximum positive moment reinforcement, but not less than 2 bars or strands, shall be continuous. At least 1/6 of the negative moment reinforcement at the support, but not less than 2 bars or strands, shall be continuous. Longitudinal structural integrity reinforcement shall be enclosed by closed stirrups. So here we don't have torsion. I will say that typically we are using closed stirrups for resisting the torsion. Assume that you have a perimeter beams, but without a torsion. Even though without torsion, you have to use closed stirrups. Why? Because if we have a loss of one support, perimeter beams will be subjected to a high torsion. That's why we have to provide a closed stirrups in accordance with 25.7.1.6 or hoops along the clear span of the beam. As you can see here, you have first of all to provide a continuous bottom bars. 1/4 of the maximum positive reinforcement must be continuous, and if you cannot provide a one continuous bar, you have to use lap supplies near the support, by the way, class B tension supplies, and the bottom bars must be anchored in the support. In addition to that, you have to keep 1/6 of the negative reinforcement with minimum 2 bars continuous. Again, you have to provide closed stirrups or hoops along the span of the beam. Again, if one of the support, if one of the support of the beam failed, this beam can be subjected to a high torsion, and the stirrups or the closed stirrups will help the beam to bridge the load to other nearby supports. So assume that this column for example, um, um, I will say that we remove this column for any reason. Uh, these continuous bars and the closed stirrups will help the beam, will support the beam to bridge the loads and transfer the loads to other nearby supports. Okay, these are closed stirrups allowed to be used for integrity reinforcement. In fact, this detail cannot be used for integrity or for torsion. By the way, this is clearly mentioned in ACI code. You cannot use this detail. By the way, I believe that in a very big transfer beams, uh, there is no way most of the engineers they are using this detail because it's very difficult. Sometimes we have 3 meter by 4 meter transfer beams. How we can provide a one continuous stirrup? That's why some engineers they are using this and they are adding here welding or couplers or anyway. But as per the code, this detail is not permitted for integrity or for resisting the torsion. Okay, here we have discussed the perimeter beams, but for interior beams, for other than perimeter beams, here we are talking about the interior beams, structural integrity reinforcement shall be in accordance with A or B. If you remember, for perimeter beams, we have three requirements must be satisfied together. But here we have A or B. A, at least 1/4, or option A, at least 1/4 of the maximum positive moment reinforcement, but not less than 2 bars or strands shall be continuous. Same like this. Here we have a continuous bars with tension lap supplies class B. Again, this restriction is only for, or this requirement is only for the bottom reinforcement. Not same like the perimeter. Now we have discussed the bottom and the top reinforcement. Anyway, we have also to satisfy the anchorage. This is option 1. Option 2, as you can see here, we have 1/4. In option 2, there is no limit for the number of bars that must be continuous, but you have or you must use enclosed closed stirrups. Sorry. So here, as you can see, no requirements for the number of bars that must be continuous, but the code need you to use a closed stirrups. As you can see, this is required for the interior beams. Some engineers or the majority think that we don't need to use the closed stirrups for interior beams because they are not subjected to a torsion. But for the integrity requirements, we have an option B that you can use closed stirrup to satisfy the integrity reinforcement. As you can see here, we don't have minimum reinforcement that must be continuous. Okay, we have also 9.7.73. The longitudinal structural integrity reinforcement shall pass through the region bounded by the longitudinal reinforcement of the column. As you can see, again, this requirement is only for the integrity reinforcement. So assume that you have a 10 bars and the number of integrity reinforcement is only 3 bars. So these 3 bars must pass through the region bounded by the longitudinal reinforcement of the column. By the way, this is, clearly requested by the code. I believe that the best solution always to keep all bars pass through the core of the columns or of the column, but this is not the case always. Here also we have 9774, longitudinal structural integrity at non-continuous supports shall be anchored to develop a field at the face. By the way, this is required when you have or when you would like to use option 1 for the beam, because here we have integrity reinforcement by the minimum 1/4. But in option B, we don't have a minimum number of reinforcement. That's why ACI, when they discuss this section, they clearly said that in this option, no need to use or to satisfy the anchorage here. By the way, I am confusing when I am looking for a provision 9.7.7.4, because here we have, or the code mentioned clearly that the longitudinal structural integrity reinforcement at non-continuous supports shall be anchored to develop a field. So you feel that always you have to satisfy this anchorage, but again, this section and this section were provided by ACI University in one of the webinars that I have attended before. Okay, for joist slab, in chapter 9 also, joist slab or ribbed slab anyway, we have also integrity requirement. For structural integrity, at least one bar, bottom bar, by the way, must be bottom bar in each joist shall be continuous and shall be anchored to develop a field at the face of support. So one bar, bottom bar, must be continuous. As you can see, class A tension supplies here is permitted, not a class B or mechanical supplies. And here, this joist bottom bars or bottom bar, because we have here only one bar, must be anchored at the support. We have discussed this before for two-way slabs, that we have to provide a bottom bars continuous through the column, and these columns also must be anchored at the edge support, and the bars of the column strip must be continuous, or class B tension supplies must be used. I think I have finished the major integrity requirements in ACI 31819. If you would like to learn more about the practical structural design workflow, you can contact me for more details. This course is in English. The name of the course is The Design Journey, and we have discussed a lot of things related to real applications of real projects in Dubai. Thank you, engineers, and I hope that this video will be useful for all of you. Thank you very much.